Yes.
Okay, thank you. So yes, I'm here to start this interesting workshop and journey that we were taking with Panasonic over the past year on compositionality and also multimodality involved in computer vision. So I think this type of introduction was given in previous versions of compositional computer vision workshops. So I'm not going to go very much in detail, but I want to mention some of our works as well. We all know that in computer vision, objects are often defined as their deformable parts as an aggregation, as a sum of their deformable parts. There are several old and new publications still in this topic of building object detection and recognition based on their part-based models. Similarly, for scenes are simply defined as aggregation of objects or scene components in the scene, and often representation of the scenes comes from this aggregation. We also investigated this topic of defining actions as sum of objects and interactions in the scene, in the video, which was the core ground for this great collaboration that we had from at Stanford with Panasonic, this home action genome work and data set that this was the grounds for a challenge in this great workshop that we are right now in. As you can see, actions can be defined as interactions between humans and objects as defined in these images. Similarly, more complex actions can be defined as a sum of atomic actions. So these atomic actions themselves become the building blocks for building larger activities, more complex activities that can compose like activities of daily living. So with this introduction, I wanted to go into details of a series of work that somehow was built on top of the previous one on using the concepts of compositionality in computer vision. Let's start with visual genome, something that most probably everybody in this workshop is familiar with. Ranjai, who's going to be talking later today, was the leader on this work. Visual genome was exploiting and investigating the use of scene graphs and scene graph representation on images. So images were simply defined with their objects and humans in the image and the interaction between objects and humans, which an example can be seen here. For example, person holding camera is characterizing one of the interactions in this image. This was further extended by having more comprehensive and more complete over complete set of interactions between objects and humans in the scene, and defining larger and more comprehensive graphs, as I said. So In visual genome, it also was argued that defining these types of scene graphs and representing images with those types of graphs enables us to actually connect images as well. Like, for example, this person in the video, in the image, sorry, in the image, this person can actually be present the concept, the object of like this entity can be present in other images, which makes it very easy and makes it meaningful to connect images with persons and in their view, very much similar to all other types of objects, creating some sort of unified representation of images, all images across the line. One of the major things that was used in visual genome was the concept of attributes on objects or humans and relationships. There are several cognitive psychology type of studies that talk about this, that attributes and relationships are processed independent of the objects themselves. Attribute and relationship violations are noticed within a very short amount of time. Relationship violations slow down object identification. This is the case for humans, and this is also the case for machines. This is an example that somehow violates the our understanding of objects and entities, because a horse cannot be moving on top of another moving car. So just some sort of cartoon for this presentation, this concept. The thing is, this is coming from this original piece of art, the Rene Magritte, The Anger of Gods. This is the commonly known piece of art for this concept. It was just redone as a cartoon by fatcat.art.com. I just used it for some for a representation of what I wanted to talk about. Okay, so after visual genome and the concepts defined and explained there for defining compositionality in images, follow-up work by our group was done for named Action Genome, published last year, which argued that action recognition is a complex task that requires understanding every single component in the scene. Therefore, these different components in the scene, especially defining different types of actions, smaller actions, and relationships, drinking from a cup, sitting in a chair, sitting at a table, looking outside of a window. What we've done in Action Genome was sampling, selecting uniformly 5 frames in each of these sub actions in the video, and then on each sampled frame, the infracted objects were localized, and as you can see, the objects and humans in the scene are characterized by bounding boxes, and we then annotated the pairwise human object relationships, formulating some sort of spatiotemporal sync
Hi, Ehsan. Can you hear me? I cannot hear you now.
Hello, can you hear me?
Yes, okay.
Okay,
I
good.
can hear you.
Sorry.
Yep.
Yes, it was probably the button. So I'll try to wrap up since we also have Ranjay here. So basically, we argued that the compositionality can also happen in the temporal domain. So we decomposed actions, more complex actions, into their temporal domain. We also looked into having multiple views of the same person doing the action at the same time. So multiple views was another component of the research. Scene graph annotations, which defined again special temporal graphs for our representation of the scene, was another big part of this this work. So, and multiple modalities of data and annotations provided us rich representation of the data, which enabled this challenge in this workshop, and then the workshop itself. For this work, we proposed a cooperative compositional method for action understanding, which was using both temporal compositionality and spatial compositionality concepts, as well as the multiple modalities in the data. The last piece of the work, which was actually a more advanced version of this work, and this is a continuing direction for us, was this compositional, more complex compositional activity understanding in general in complex scenes, which we argued that with shorter activities or entities composing more complicated activities, we needed a partonomy-based representation, showing that activities, sub-activities, and atomic actions can create some this type of hierarchy, and then the special compositionality can be defined in the lowest level of this definition, which led to this publication, MoMA, multi-object, multi-actor action parsing framework, which actually created this very cleanly defined compositionality in space and time. Here we define the compositionality with the partonomy-based and taxonomy-based compositionality, the terminology. As you can see, for example, activities are composed by sub-activities, and sub-activities by atomic actions. Atomic actions themselves are composed by their special configuration, which we defined through action hypergraphs. This shows a partonomy representation of activities in time, but at the same time, we had entities which were actors and objects, and they have each of them different types, relationships of static and dynamic relationships, each of those again having different types. So basically, compositionality in terms of parts and taxonomies were introduced in this work. Here, we extended the concept of spatial temporal graphs, scene graphs, into action hypergraphs, because now when we have multiple humans or multiple objects, the relationships will be higher order than just pairwise type of relationships. And therefore, we defined hyper edges and after that action hypergraphs. Features in this data was multi-object, multi-actor nature of it, definition of hierarchical representation, and we also had actor roles now that we have multiple actors, where we had actor roles. For the method, we developed a hypergraph convolutional module alongside the video stream, defining multiple output heads for different tasks in this work, which actually defined our higher level action parsing task. On the side, we also had hierarchical action classification, role classification as side tasks. An interesting piece of result was we could actually, based on our recognition and extraction of the graphs, we could actually build average graphs for our the action. So these are action average graphs for dining service and bike lesson throughout the data set that we had. I would like to here refer everybody to the website to check out the 2 tasks that were defined using this home action genome data set, interesting tasks, and the videos of the winners and introduction of the tasks are all on the website as well. Now I would like to leave the rest, invite everybody to listen to the rest of the live keynote talks. We have Ranjay and Anju and Alan also as a recorded video that will be posted on the website. Thank you for listening. We started a little bit late and I took more than what I should have, but I'm glad that we have Ranjay here.